Now let us look at memory cells. So memory is a far denser storage technology than flip-flops, and so that's the reason it's used in structures inside the processor to actually store a lot of data, not just one bit or several bits, but thousands or millions of bits. So the two kinds of memory technologies that are normally used are SRAM static RAM cells and DRAM dynamic RAM cells. So an SRAM cell works like this, that so what is the main philosophy here? The main philosophy is that we want to reduce the number of transistors that are required to store a single bit, because we'll be saving millions of bits, possibly billions of bits. So that's the reason we need to keep the number of transistors as low as possible, and we also want to provide a memory technology that is as fast as possible. So what we do is that to reduce the number of transistors, instead of using cross-coupled NAND gates, as was the case in flip-flops, right? We use a cross-coupled pair of inverters, which does the same thing, but we need some additional circuitry, as we shall see. So in this case, this is an example of a cross-coupled pair of inverters, where the output of one inverter is connected to the input of the other, and similarly the output of the lower inverter is connected to the input of the upper inverter. So let's say value x is stored here, then the complement of x is stored on the other side. So this structure by itself is potent enough to store the value of one bit. And how many transistors does this require? So if you would recall, the structure of an inverter was that it required two transistors, a PMOS transistor and an NMOS transistor. So since one inverter requires two transistors, we need a total of 4 transistors in this structure. But however, this much of circuitry is not enough to read and write values into this structure. So what we need to do is that we need to have something else to actually read and write into this structure. So the something else is like this. So let's first consider a cross-coupled pair of inverters, which is here at the bottom. And so here, as shown in the previous diagram, we have 4 transistors, 1, 2, 3 and 4. And but let's sort of isolate this as a black box. So we'll need 2 more transistors. So what do the transistors do? So we have one transistor W1 and one transistor W2. These are simple NMOS transistors. So when the so these are called word line transistors. So when the word line is set to 0, at that point the NMOS transistors are off. So it is like that this memory cell is disconnected from the rest of the world. So it is not possible to read its values, neither is it possible to write its values. So the value that is stored inside the memory cell will be maintained. On the other hand, if the value of the word line transistors is equal to 1, then this transistor is on, so this line gets connected, and pretty much what we see is that this 4 transistor cell is connected to the outside world and is possible to both read and write its values. So let's consider writing first. So since we have 2 inverters, whatever value is saved here, the complement of the value will be saved on the other side. So it's a symmetric structure. So one copper line connected to one side is called a bit line, and the other one is also a bit line, but it stores the complement of the value. So both of these copper wires are called bit lines. So one stores the value and the other stores the complement or the value stored inside the cell. So if we want to write, let's say 1 into the cell, we set this bit line to a logical 1, which is the supply voltage, and we set this bit line to a logical 0, which is ground. So in this case, if the voltage drivers are strong enough, then the 4 transistor cross coupled pair of inverters will be programmed such that the value saved over here is 1 and the value saved at this point, which is also the same as the value stored in these points, right, is 0, right, and here it is 1. Similarly, if you want to save 0 in the 4 transistor SRAM cell, in the 4 transistor cross coupled pair of inverters, what we need to do is that we need to set, of course, we need to set the word lines to 1 to enable the SRAM cell. Then we need to store a 0 over here, drive the bit line to a 0, BL to a 0, and BL bar we need to drive it to a 1. So that will set the values, the voltages at these points to 0 and the voltages at these points to 1. So writing is easy, reading is also easy. So in this case, what we do for the purpose of reading is that we enable the transistor by setting the word lines to 1, and we don't use any circuitry to explicitly drive the voltage of BL and BL bar. Instead, we allow their voltage to become the same as the voltages that are stored inside the cell. For example, if this voltage is a logical 1 and this is a logical 0, so over time the voltage of BL will become a logical 1 and the voltage of BL bar will become a logical 0, and thus we can infer that 1 is stored inside the cell. That's how we will read. Alright, so what are the important points that need to be taken care of? So our basic cross coupled pair of inverters had 4 transistors. Now we have our 2 word line transistors. 6 transistors are there now in each cell, and then these are connected to 2 bit lines. So an alternative representation of an SRAM cell looks something like this, where we have a pair of inverters and the voltage at one side is V and the voltage at the other side is a complement of V. So then the word line transistors can be treated as switches, and this entire 6 transistor cell called an SRAM cell, it's a static, it's called a static RAM cell. We'll see why when we discuss dynamic RAMs. So they drive the voltage of BL and BL bar. In the read mode, the bit lines are kept floating. So what does floating mean? Floating means that they are not explicitly connected to either the supply voltage or the ground voltage. So we allow the voltages V and V bar to propagate to set the values of the bit lines BL and BL bar. So that is how we can read the contents. For writing, what we do is that we again enable the word lines, and then we explicitly set the voltages of BL and BL bar such that this 4 transistor SRAM cell gets appropriately programmed. Now let's create an array of SRAM cells. So to create an array of SRAM cells, let's see what needs to be done. So what we do is that we create one SRAM cell and we arrange them in a matrix form. So let all the SRAM cells on a single row be connected via the same word line, and let the rest of the SRAM cells along a column be connected to the same pair of bit lines. So the first thing that we do, number 1, this is like step number 1. So let's assume that we have 128 rows. So we need to enable one of the rows. So how do we do that? We use a decoder to set only one word line to 1, which is true based on the address, and the rest are 0. So let's assume that each row can store one integer, which is 4 bytes. So since 4 bytes is 32 bits, we'll need 32 SRAM cells. And let's assume that there are 128 such rows. So the address of a 128 is 2 to the power 7. So what can be done is that we can send a 7-bit address the 7-bit address can be used in the decoder to set one of the word lines to 1 and the rest will remain 0. So let us assume that this word line gets set to 1, which means that this entire row gets enabled and the rest of the SRAM cells in the other rows are disabled. So now what we do is that this particular row, after it is enabled, so mind you, only one row can be enabled at a time. So after doing that, all the SRAM cells are enabled and they will be setting the values of BL and BL bar. Subsequently, what we can do is either we can consider the values in all the SRAM cells, or let's say we want to read only 2 bytes. If we want to use 2 bytes, we can use a pair of multiplexers such that for this example, if 4 bytes are coming in, we can choose the 2 bytes that we need to read. And then this can go out. And same is the case for writing as well. If we want to write to 2 bytes, then we will have driver circuits that can help us that can essentially help us set the voltages as we shall see of BL and BL bar. And then the multiplexer circuit over here will enable certain SRAM cells such that we can read or write them. For example, if we just want to enable this and this, then the multiplexer will only ensure that the outputs of these cells actually flow out of it. So how do we operate an array of SRAM cells? So an array of SRAM cells will have 2 modes, a write mode and a read mode. In the write mode, we'll use a driver circuit to set the values of the pair of bit lines BL and BL bar. Simultaneously, we need to enable the word line from the decoder. The values in BL and BL bar will get transferred to the SRAM cell, thus affecting a write. In the case of a read, what we need to do is the first step, disconnect the bit lines from the supply voltage and from ground using transistors. So basically what we can do is we can have a circuit of this type where this is the supply voltage, right? This is VCC, the supply voltage, and we'll have a transistor. So here if we set the gate voltage of the transistor to 0, essentially this line is disconnected from the supply voltage. So we say that it is floating, right? If a certain copper wire is disconnected from supply as well as the ground, we say that the wire is floating. Then we enable the word line. Once we enable the word line, right, so there are a pair of bit lines. Then there is the SRAM cell here in the middle, and then there is a word line. So once we enable the word line, the SRAM cell gets enabled, and the values of BL and BL bar get set to logical 1 and 0 depending upon the value stored in the SRAM cell. So there are some issues with this, very simple design. The first is, so let's go back. Let's actually go back to this particular slide once again, remove all our annotations, and look at it once again. So we have an array of SRAM cells. So mind you, this array can be very big. So the array can have literally thousands of rows. So if you want me to give a typical example, so let's assume that I have a 256 kilobyte SRAM array. So 1 kilobyte is 2 to the power 10 and 256 is 2 to the power 8. So total there are 2 to the power 18 bytes. So the number of bits would be 2 to the power 18 times 8, which is 2 to the power 21. So even if we try to make a nice structure which is sort of looks like a square, and we have 2 to the power 11 rows here and 2 to the power 10 columns here, we will still have 2048 rows. So which means that one SRAM array is a very big structure, and to each bit line, which is a thin copper wire, 2048 SRAM cells are connected. If that is the case, this long wire will have a lot of resistance as well as capacitance, and the RC delay, so if you recall what you were taught in first year, if a wire is very long and a wire is connected to a lot of other elements, its resistance and capacitance will be high. So driving the voltage of the wire either towards the ground or towards the supply voltage will take a lot of time. Right? So basically, why is the wire long? The wire is long basically because a lot of SRAM cells, literally thousands of SRAM cells are connected to it. So this will make the SRAM very, very slow, and the question is, can we do something better? We definitely can do something better, but let's start with this idea. So let us do one thing. Let's consider the simple SRAM cell, which has 6 transistors, which is connected to two very, very long bit lines. They are called BL and BL bar. So, and it takes a long time to charge both of these bit lines to either 0 or 1. So let's do one thing. Let us pre-charge both the bit lines to, let's say, 0.5 volts, where the assumption is that a logical one is 1 volt, using very, very strong pre-charge driver circuits. So what we do is that before we begin reading, so mind you, reading is slow, writing is not slow. The reason writing is not slow because we can connect very strong, write driver circuits to the BL and BL bar bit lines, right? So D is for a driver, such that you can quickly drive them to a logical 0 or logical 1. But that is not the case when you are reading. The reason that is not the case when you are reading is because this small little SRAM cell has to drive the voltages of the bit lines to either 0 or 1. So what we do is that before we start to read, we have these pre-charge circuits, right? P is for pre-charging, which are connected to the BL and BL bar lines, and we quickly drive them up to 0.5 volts. Where the assumption is that a logical 1 is 1 volt. So we drive them to the midpoint. Once the voltage has reached 0.5 volts, then using a transistor, by programming a transistor, we disconnect both of these pre-charge circuits, and the lines are now floating, and we enable the word line. So what will happen is that, so initially t equal to 0, the voltage at both the bit lines is 0.5 volts. Subsequently, one of the bit lines will move towards 0 volt. So let's assume that this bit line is moving towards 0 volts, and the other bit line will move towards 1 volt. So now the question is that if we know that ultimately one bit line will reach 1 volt and the other one will ultimately reach 0 volts, the moment we have made this determination, we don't really have to wait for the bit line to reach 1 volt and the other one to reach 0 volts, right? So it is similar to the fact that assume a student is not doing well and a course has, let's say, 5 exams, and after the first 2 exams the student has found out that there is no hope of passing the course. It is not necessary for the student to sort of wait till all the 5 exams are over, right? The student can at that point withdraw from the course. So it's similar, like in a game of chess, you actually don't wait for the king to be killed. Long before the king is killed, typically one side realizes the game is up and they resign. So the case is similar here. We start by pre-charging both BL and BL bar to 0.5 volts. Subsequently, one of the lines will move towards 0 volts and the other line will move towards 1 volt. So let us monitor the difference in voltages between the bit lines, right? So let's have a simple circuit over here whose only job is to subtract the voltages of VBL and VBL bar, right? So we are monitoring the difference. And in this case, Again, this sort of a repeat of what I said. Should we wait for one of the bit lines to reach 0 volts and 1 volt? The answer is no. So this is what we do. Let's monitor the difference delta, which is voltage of BL minus voltage of BL bar. So there can be a little bit of electrical noise in the system. Why is this the case? You would have typically seen that if you turn on some electrical appliance like a microwave oven or a washing machine, there is a little bit of noise in your phone. So that is basically because a little bit of inductance happening. So it's possible that inside an SRAM also we have a little bit of electrical noise. So let us define a noise threshold and let's call it T. Right, so this is the amount of random noise that can come on a copper wire. So the moment the absolute value of the difference in voltages is beyond that noise threshold, which means that this is a real difference, it's not a random difference, we can declare the result. Right, say the voltage of BL, so assume that we start at 0.5 and 0.5. After let's say 1 nanosecond, let's say that the voltage of BL becomes 0.6 volts and voltage of BL bar becomes 0.4 volts. So at this point, we'll be very, very sure that 0.6 will ultimately go till 1. Similarly, at this point, we'll be very, very sure that 0.4 will ultimately go till 1. So it's also the same as declaring the results of an election, right? So let's assume that there are two candidates and one candidate is just racing ahead. So see, at the beginning we will not be able to say, because the candidates might be going neck and neck and there might be some noise in the counting process. So maybe the votes for one candidate are sort of disproportionately mixed up. But gradually as the time passes, clearly one candidate will emerge to be the winner, and once we are sure, we can pretty much declare one candidate as the winner and in a sense not wait for all the votes to be counted. So it's very similar over here. So let's assume that the amount of noise that the system will introduce is very small. So maybe from 0.5 when it reaches 0.6 and the other one reaches 0.4, we can be sure that in this case BL will reach logical 1 ultimately. We don't have to wait, and BL bar will reach, oh I'm sorry, this should be logical 0. Yeah, this should be logical 0. It'll reach 0 volts ultimately. We don't have to wait. So what we can do is that at this very point, at 1 nanosecond, we can declare the result. So this is a very, very fast way. And it's a very standard approach in hardware, where what we do is that we, instead of waiting for the bit lines, one bit line to get fully discharged and one bit line to get fully charged, we monitor the difference. Once we are sure, we declare the result. In this case, if the difference is positive, we infer a logical 1. Otherwise, we infer a logical 0. This is a very, very fast method of reading, because assume that for one line to reach logical 1 and the other to reach logical 0, it would have taken like 20 nanoseconds. In this case, in 1 nanosecond, we have the result. So what does an array of SRAM cells now look like? We have our previous diagram. The only additions are as follows. So we have a set of precharge drivers, as you can see on the top. So what these precharge drivers do is that they help in precharging the bit lines before a read. Subsequently, after the column multiplexer, so let me just repeat, what a column multiplexer does is that it helps you choose a subset of columns that you want to read or write, because typically if the array is very large, we don't want the array to be like one long strip. We want it to be nicely organized as a square for certain circuit design considerations. So that makes it necessary to choose a subset of SRAM cells within each row, right? A subset of columns within each row. So that's the reason we have a multiplexer over here. And this is connected, so the pair of bit lines comes out. So for the case of a write, we can use these write drivers, which are very powerful circuits, to set the values of the bit lines to 0 or 1. For the case of a read, we have this simple circuit called a sense amplifier. So the role of the sense amplifier is basically to monitor the difference between the voltage of the one bit line minus the voltage of the other bit line. So it just monitors the difference. Once the difference increases an acceptable threshold, it declares the result either a logical 0 or a logical 1. So what are the only additions in this most important circuit? Well, we started out with an array of SRAM cells and a decoder to choose the right row by enabling the word line. We also had the column multiplexer demultiplexer to basically choose a set of columns. The additions are the set of precharge drivers that help precharge the 2 bit lines, a set of write drivers in this diagram to basically set the voltages of the bit lines, and some very specialized circuits called sense amplifiers that help monitor the difference in voltages between the bit lines such that we can declare a logical 0 or a logical 1, depending upon which way the difference is going. Now let's consider a DRAM cell which is even smaller than an SRAM cell. So smaller is the cell, more compact it is. So for the same area, more cells can be packed, so the memory can be more dense. But also smaller is the cell, the lesser is its power to actually drive the bit line to a 0 or 1. So in a sense it's also slower. So that also needs to be kept in mind, that latches and flip-flops are very fast because there are more transistors, and as a result it is easier for them to program them. You don't have bit lines. SRAMs are still fast enough, but DRAMs are slow, and we shall see why. So the reason for this is that instead of having a cross-coupled pair of inverters, the main circuit in a DRAM is a capacitor. So charge is stored across the capacitor. So if the voltage across the capacitor is close to the supply voltage, we can infer a logical 1. But if the voltage across the capacitor is 0, which means at this point here is close to a logical 0, the potential is close to 0 volts, we can infer a logical 0. So that's the only structure. There is no cross-coupled pair of inverters. So we shall see that there is, there are good aspects to this and there are bad aspects to this. But this is pretty much the only structure inside the DRAM cell, a single capacitor. And the way that we control access to it is that we have a single transistor here, which is controlled by the word line. So the word line is set to 1. We can assume that the switch is connected and the capacitor is directly connected to the bit line. And here also there is a single bit line. Instead of 2 bit lines, there is a single bit line. So we infer the value of the voltage stored across the capacitor by taking a look at the voltage of the bit line. Also for writing, what is done is that when we write, we connect a driver circuit to the bit line. Right, the connection is again done with the help of a transistor switch, and the driver circuit can do one of two things. So if it pumps in charge into the capacitor and its potential increases, then we are trying to write a logical 1. Otherwise, if it drains out charge from the capacitor, then we are writing a logical 0. And once the word line transistor is disabled, disabled basically means that we set its voltage to 0, then the capacitor is disconnected, right? You can sort of think that the switch is disconnected. So whatever is the voltage across the capacitor will remain. So now let's consider an array of DRAM cells. So this is very similar to an array of SRAM cells as we had seen. There is a single bit line, right? So that's one difference. In an SRAM array, there were 2 bit lines. Here is a single bit line. For writing, we enable the word line and charge the bit line with a driver circuit, and then the bit line transfers the charge to the capacitor. For reading, we do something very, very similar to what we had done in the case of SRAMs. We pre-charge the bit line to 0.5 volts. So where again the assumption is that a logical 0 is 0 volts. So which this assumption is most of the time correct actually. Nowadays most of the supply voltages are close to 1 volt. So we pre-charge the bit line to half of the supply voltage, which in this case is 0.5 volts. We enable the word line and we monitor the difference of the voltage with respect to 0.5 volts. So basically, if this is the bit line, so we have a simple, oh, I'm sorry, I shouldn't have added the BL bar. Just a bad habit from the SRAM days. 1 second. Yeah. So if this is the bit line, we will have a sense amplifier, which is essentially a comparator, and the other signal that is going into it is a fixed signal, in this case of 0.5 volts. So we essentially monitor the difference, and the idea is the same. Once the difference exceeds a threshold, we declare the result, whether it's a logical 0 or a logical 1. And what is the threshold? The threshold is expected to be a small value of the order of several millivolts. So that will be the amount of noise that is introduced in the wire because of external electromagnetic fields. That's all. So that's the only difference, that instead of comparing BL and BL bar, we compare a single bit line with another fixed voltage, which is 0.5 volts. And we see whether the voltage is going up, shooting above 0.5 or going below. And based on the direction, we infer the value stored in the DRAM cell. So there's a problem. So basically, we initially had a cross-coupled pair of NAND gates. So in a flip-flop, if you would recall, in a flip-flop, we had a cross-coupled pair of NAND gates. So since there were more transistors, it was possible to drive in more current. There were more paths from the ground and VCC. And also, it was easier to program these devices. In comparison, an SRAM cell is a cross-coupled pair of inverters, and you have bit lines and so on, which make it slow. And even slower are DRAM cells, which have a single capacitor. But there is a problem with it. So the problem is that after every read operation, so let's assume that the capacitor throws a logical 1, we lose some charge from the capacitor. So this means, and also, right, so this should be, we lose some charge definitely. So the charge is shared between the capacitor and the bit line, and on a regular basis, charge from the capacitor leaks out, right, on a regular basis. Hence, it is necessary to, so what will happen? So what will happen is that, let's say at t equal to 0, if we store, let's say, time equal to 0, we store 1 volt across the capacitor. What will happen is that maybe at t equals 2 nanoseconds, a little bit of, see, no dielectric is perfect. So you would hope that, between the two parallel plates of a capacitor, there is no leakage. But there is always some amount of leakage via the capacitor, little bit of current. And even the transistor, when it is turned off, there's still a little bit of leakage, so a little bit of current that flows out. So maybe after t equals 2 nanoseconds, the voltage can be 0.8 volts. And maybe after like 20 nanoseconds or 50 nanoseconds or 1 microsecond, you will find that the entire voltage across the capacitor has disappeared. So this will cause an error. That's the reason it is necessary to periodically read each and every DRAM cell and read the data back, and write the same data back. For example, if we write 1 to a DRAM cell, and let's say that after 50 nanoseconds we read it, and find that the voltage across the capacitor is 0.7 volts. That is fine, we can still infer a logical 1, but we will also be aware that the voltage has decreased. So what we will do is we'll write a logical 1 back again, and in this case the voltage across the capacitor will again become 1 volt. So this sort of periodically compensates for the charge that is leaking out of a capacitor, because dielectrics are not perfect. And also if there is a read operation, then basically the charge will get shared between the long bit line and the capacitor, right? And since the charge gets shared, the voltage across the capacitor will decrease. So that's the reason it is necessary that after every read, we need to write the data that we read back again, and also periodically we need to read each and every DRAM cell and write the same data back. So this process is called restoring the value of a single DRAM cell, and the overall process where we read the entire DRAM array. So where we read, so given an entire DRAM array, right, where we read the contents of the entire DRAM array and refresh all the contents, is known as a DRAM refresh. It's known as the DRAM refresh cycle, where all the contents are read and again they are written back, right? So it's not that we read all of it and then write it back. We read, let's say, 1 byte and then we write back that same byte, or we read 64 bytes and we write back the same 64 bytes. So it's definitely not done at the entire array level at one go, but the aim is that periodically we read some lines and then again write them back to sort of restore their voltages across the capacitors to the maximum levels, to the highest levels. So here is what an array of DRAM cells looks like. It is very similar to an array of SRAM cells. The only differences are that there is a single bit line instead of multiple bit lines. The address and the decoder part are all there, and the cells are organized as a matrix. The column multiplexer, demultiplexer is also there. And addition is the refresh circuitry, right? So the refresh circuitry, what they do is they periodically read values from each row and write them back, right, to restore the original voltage levels. For writing, we have write drivers, which are fast circuits to set the values of the bit lines. And for reading, we have sense amplifiers, similar to the case of SRAMs, where we read the values of a DRAM cell out. So rest everything is same as an SRAM array. The only difference is we have a single bit line and we have refresh circuits. Now let's consider one more type of cell called a CAM cell. So the idea is that instead of enabling cells by their address, can we find them by their contents? So let's go back to the previous slide. So let's assume that there are only 4 cells in each row. So let's assume that the problem is that we want to find the row that contains 1, 0, 1, 1. And let's, for the sake of simplicity, assume that only one row contains this particular value. The question is that can we find out which row it is? So one simple solution is that we just, like a for loop, we read the contents of each row and we compare. We read and compare, we read and compare, till we find the row. That is possible, but what's the problem? The problem is that we need to read the contents of the entire SRAM array or the DRAM array. So which is not a good idea. We can do something better, right? So this is called content-based addressing, and a CAM cell is called a content addressable memory, where you're trying to find it by its content, not by its address. So mind, if the address is coming, the decoder is setting one of the word lines to 1, and then that row is getting enabled. But in this case, we want to see if there is any row whose contents are same as the contents that we want. So we design a CAM cell, which is nothing but a simple SRAM cell plus more. So this part that you see in this dotted rectangle is a simple SRAM cell. Subsequently, what we have is that we have these additional connections over here, where we get in the values, so we call them V and V bar. V is the value and V bar is its complement. And we get in the values that we want to compare this against. So this is a single bit. We'll compare it with a single bit. So this value V will go into transistor T1, and we want to compare value V with another bit value called A. So A bar, the complement of A, is sent to transistor T2 over here. So this is basically the complement of A, and this is the value V. Similarly, this is the value V bar, the complement of V, and this is the value A. And so these transistors are connected in series. So one side of them is connected to the ground, and the other side is connected to this blue wire called the match line. So let's see what it is. So let's consider the pair A and V bar, right? So transistors T3 and T4. And let's consider the case when A is equal to V. So if A is equal to V, one of the values has to be 0, right? So let's assume that A is 1, then V bar has to be 0. If A is 0, V bar has to be 1. So one of them has to be 0. So either T3 or T4 is off. One of them is off. So essentially this path over here is pretty much disconnected from the ground, right? Because of any one of these transistors, T3 or T4, one of them is off. Similarly, in the pair A bar and V, one of the values has to be 0. So either T1 or T2, one of them is off. So you can find out, you can use values. So if A is 1, then A bar is 0. If A is 0, then since A is equal to V, V is 0. So one of these values is 0. So which means one of T1 or T2 is off. So even this path is turned off, which basically means that for this particular CAM cell, which has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, which is a 10 transistor CAM cell, the match line is not connected to the ground, right? So it is in a sense floating. So it's not connected to the ground. So this is what we get to find, just to summarize, that when A is equal to V, the match line will be disconnected from the ground terminal. Fine. So let's see what happens when A is not equal to V. So when A is not equal to V, let's see what is the case. So we say, so let's assume what we claim is either A comma V bar or A bar comma V is equal to 1 comma 1. So let's see why. So let's assume A is 1 and V is 0. So in this case, A is 1 and V complement is 1. So this pair is equal to 1 and 1. Assume that A is 0 and V is 1. So in this case, A bar is 1 and V is 1. So basically, irrespective of the value of A, one of the pairs, A, V complement or A complement and V, one of the pairs is equal to 1 comma 1. So with no loss of generality, let's assume that T3's input is 1 and T4's input is 1, which means both of these transistors are turned on. So we basically have a direct connection from the match line to the ground, and this means that if A is not equal to V, there is a mismatch, and in this case the match line will be driven to 0 volts because it is connected to the ground. So what do we understand? We understand that if A is equal to V, then the match line is kept floating, which means it's not connected to the ground. And if A is not equal to V, then the match line is driven to 0 volts. Right? So that is the important takeaway point from this particular slide, that if there is equality between A and V, then we are fine, the match line is still kept floating, otherwise it is driven to 0 volts. So given this, we can design a very simple circuit. We can design an array of CAM cells, which looks very, very similar to an SRAM array, absolutely no difference. So let's consider a regular SRAM array. So essentially all of this part that you see, right, all of this part, is a regular SRAM array. The only difference is that we have this additional cam mode where pretty much all the so basically it is all the word lines in this case can be turned off. It's not a problem. And the only difference is that instead of an SRAM cell, we have a cam cell over here, and it has its regular bit lines as inputs because a cam can work as an SRAM as well, and you can see write drivers and sense amplifiers and everything else. But the only extra part other than the cam cell is connections to these values. So for the first column, we compare it with the first bit A1. So one side we connect to A1 complement and other to A1, as was shown in the previous figure. Similarly, the second column we connect it to A2 complement and A2. And similarly, the nth column we compare it with the nth bit. And all of the cam cells are connected to a single match line. So here is what we do. We precharge all the match lines to, let's say, a logical 1. Subsequently, let's consider one of the match lines. So let's consider maybe the first one. So let's assume in this case, there is an inequality in the sense the value stored in the cam cell is not equal to A2. So what do we know from the previous slide? When it's not equal to, the match line is driven to 0 volts. So immediately the value on the match line will be 0. So what did we do? We precharge all of them to 1. Then we disconnected the precharging circuit and we started comparing. So whenever there is a mismatch even in a single bit, all of these match lines will get driven to 0 volts. But let's assume for this row, all the bits match, right? There's a complete 100% match. Then the match line will not be driven, this match line will not be driven to 0 volts. It will maintain the value that it was precharged with, right? Because this is not connected to ground. So it will maintain the value that it was precharged with, which was a logical 1, right? And so what do we get to see? Now when we put in all of these match lines to a OR gate, all the rows that do not match will have a 0 and all the rows that do match will have a 1. So let's assume with no loss of, let's assume for the simple case that only one line matches. So what we will see is that, okay, let's first assume that one line matches. So if one line matches, then the OR of all of these functions is a 1 and the net match is equal to 1, which means that there is a match. Now let's assume that no line matches. If no line matches, all the values are 0. If all the values are 0, the OR gate at this point will compute a 0. So what we can pretty much do is that by ORing all the match lines, we can find out if we found a match in the cam array or not. Subsequently, what we can do is we can use an encoder to find the ID of the row that matched. So if you recall what is an encoder, so in an encoder pretty much it takes 2 to the power n inputs, where one of the inputs is 1, the rest are 0. Subsequently, you have an n-bit output which gives the ID of the input that matched. This is exactly what we need over here, that we can use an encoder to find out. So for example, if this is the second one, then the output will pretty much be 0, 0, 0, 1. Right? So where the first line we are assuming is all zeros. So this is a match in the second row. It will be 0, 0, 0, 1. Now assume that multiple rows match. So we can always have some sort of a priority scheme of choosing one row over the other and use a priority encoder. So that is relatively straightforward, but if you want to do further reading, you can take a look at the term called the priority encoder on Google, and you will see a circuit where if there are multiple match lines that are true, then how do you choose one over the other, right? But in a simple case, if you assume that there is a single match, then the encoder will tell you the ID of the row that matched. Alright, so this finishes the end of this chapter, a very short, quick 3-hour lecture on digital logic. So what did we cover? We covered basics of transistors. So maybe I can write down. We covered basics of transistors. We looked at logic gates and or logic gates. So you'll find something called Carnot maps in the book. So I have not covered that, but that you'll find in the book. Then we covered latches and flip-flops, where our definition is that a flip-flop is basically a latch with a clock. And then we looked at memory cells, right? And in memory cells, we looked at three kinds of cells. We looked at SRAM cells, which is a cross-coupled pair of inverters connected with bit lines. And the main idea was that it is true that we connect an SRAM cell with two bit lines, right? If this is the SRAM cell, BL and BL complement. And the reason is such that we can take the difference of the voltages between the two bit lines. The advantage of taking the difference is that we don't have to wait till a bit line goes till logical 0 or 1. From the direction in which the voltages are moving, we can infer the value stored in the SRAM cell. The other kind of cell that we looked at is a DRAM cell. So a dynamic RAM cell, the data is stored in a capacitor. So here there are some problems where the capacitor can leak and so on. So it's necessary to periodically read the value and write it back again so that the voltage can be restored to normal levels. So this is called the process of refreshing. And finally, we looked at CAM cells, content addressable cells, where we have a 10 transistor CAM cell and a match line. Alright, so in the next chapter, we'll take a look at computer arithmetic, which is methods to do addition, subtraction, multiplication in hardware.